In 2020, a graduate student at Cornell University was staring at a plot of data sent back from a machine 15 billion miles away, when she noticed something that shouldn't have been there. A faint, steady, almost musical hum, buried deep in the readings of an instrument that had been quiet for years. Her first thought wasn't excitement. It was doubt. In her own words, describing the moment later, "Am I starting to see things?" She wasn't. What she'd found was a real signal, coming from a region of space no instrument had ever sat inside before. Interstellar space, the true void between star systems, being sampled in real time by a spacecraft called Voyager 1. And for the better part of 3 years afterward, nobody could say for certain what was actually causing it. Not because the signal was exotic or alien or unprecedented in some dramatic science fiction sense. The opposite, actually. The problem was that this faint, persistent hum could be explained by two completely different, perfectly ordinary physical processes, and distinguishing between them meant solving a genuinely difficult problem in plasma physics using data from a 40-year-old instrument never designed to answer this particular question. This is the story of that signal, where it came from, why it took years to explain, and what scientists now believe they've finally figured out about the sound of the space between the stars. I'm Jameson Evans, and today we're tracing this mystery from the moment it was accidentally discovered to the quiet, technical breakthrough that explained it. Subscribe now, because the answer says something genuinely new about what fills the emptiness beyond our solar system. To understand this signal, you first need to understand the instrument that found it, and why it was even listening in the first place. Voyager 1 launched in 1977 carrying an instrument called the Plasma Wave System, built specifically to detect electric fields generated by charged particles in space. For most of the mission, this instrument had one very specific, very useful job: listening for plasma oscillations triggered whenever a shockwave from the sun, the pressure wave from a solar eruption, rippled outward through the solar system and eventually slammed into the surrounding interstellar medium. Those shock-triggered oscillations let scientists calculate the density of the plasma out there, but only when a shock happened to pass by, which was rare, unpredictable, and left long gaps of total silence in between. For most of the mission, this instrument had one very specific, very useful job: listening for plasma oscillations triggered whenever a shockwave from the sun, the pressure wave from a solar eruption, rippled outward through the solar system and eventually slammed into the surrounding interstellar medium. Those shock-triggered oscillations let scientists calculate the density of the plasma out there, but only when a shock happened to pass by, which was rare, unpredictable, and left long gaps of total silence in between. In 2012, Voyager 1 crossed the heliopause and became the first human-made object to leave the bubble of solar wind that surrounds our solar system entirely, entering true interstellar space. From that point on, the plasma wave system wasn't just monitoring the solar system's edge anymore. It was sitting inside a region of the galaxy no instrument had ever directly sampled before, waiting for the next rare shockwave event to give scientists a usable measurement. That's what made 2017 onward so unusual. Between the widely spaced, dramatic shockwave events the instrument was built to detect, something else started showing up in the data. Something continuous, something that didn't need a shockwave to appear at all. Nobody was specifically looking for it. It surfaced almost by accident. Buried in years of routine data, nobody had reason to scrutinize that closely, until one person did. That person was Stella Koch-Acker, a PhD candidate at Cornell University working with the Voyager data. Going through months of readings, she spotted a signal that was almost too subtle to trust. A weak, narrow band of emission sitting right around the local plasma frequency, present not for a few hours after a shock event, but continuously for years. It didn't fit the pattern the team was used to looking for at all. When the discovery was published in Nature Astronomy in 2021, it represented something genuinely new: the first steady, continuous measurement of interstellar plasma density that anyone had ever obtained, rather than the scattered, shock-triggered snapshot scientists had relied on before. Instead of one data point every few years, this gave them a measurement roughly every few days. That, on its own, was a real breakthrough, a kind of ongoing, low-resolution weather report from inside interstellar space instead of an occasional single photograph. But the paper was honest about something else. Nobody was sure exactly what was producing the signal. Two candidate explanations were on the table, and they described genuinely different physical situations. The first possibility was thermally excited plasma oscillations, essentially the natural, spontaneous vibration of the interstellar plasma itself, a kind of ambient jitter produced just by the plasma existing at a particular temperature and density. This would be interesting, but it would fit inside physics that was already well understood. The second possibility was something called quasi-thermal noise, or QTN, a different and more specific mechanism, caused by the small-scale thermal motion of individual electrons within the plasma, detected as tiny voltage fluctuations on the instrument's antenna. QTN had been well studied before, but almost entirely inside the solar wind, the relatively dense, warm plasma environment much closer to the Sun. Whether the same physics applied cleanly out in interstellar space, a much colder, thinner, and stranger environment, was a genuinely open question. Why this was harder to solve than it sounds. Here's where the story gets technically interesting instead of just puzzling. Quasi-thermal noise theory had been developed and tested for decades inside the solar wind, using instruments and conditions that matched that environment well. Applying the same theory to interstellar space wasn't simply a matter of importing the equations wholesale. The plasma out there is far colder and far less dense, and Voyager's antenna, a piece of 1970s hardware never designed with this specific measurement in mind, was short relative to the physical scales involved. Using an instrument built for one job to answer a very different question, decades later, in an environment nobody had planned for, is not a straightforward translation. It's closer to using a ruler designed to measure centimeters and trying to carefully extract a measurement in kilometers. Not impossible, but requiring real caution about where the tool's assumptions start to break down. That caution turned out to be justified. Over the next 2 years, a team of plasma physicists, Nicole Meyer-Vernet and colleagues at the Observatoire de Paris, working alongside Voyager instrument scientist William Kurth at the University of Iowa, went back through the data with quasi-thermal noise theory specifically adapted for the interstellar environment. Their conclusion, published in 2 separate papers in the journal Astronomy and Astrophysics in 2022 and 2023, was that the signal was indeed consistent with quasi-thermal noise, but with an important refinement that the simplest version of the theory had missed. The specific shape of the signal, they argued, wasn't fully explained by the ordinary thermal motion of the bulk interstellar plasma alone. It required the presence of a small population of unusually fast-moving electrons, what physicists call superthermal electrons, sitting on top of the much larger population of ordinary, slower-moving plasma electrons. In effect, the interstellar medium wasn't behaving like a single, uniform gas of particles all moving at the same characteristic speed. It contained a small, energetic minority of faster particles mixed into the bulk of the plasma, and it was that minority population that gave the signal its distinctive, persistent shape. The same 2023 paper carried a pointed warning for the field. Some earlier attempts to interpret this kind of signal in the interstellar medium, by researchers applying quasi-thermal noise theory without accounting for the specific differences between the solar wind and interstellar space, had made errors misreading exactly the kind of subtle features this signal displays. Getting the interpretation right required treating the interstellar medium as its own distinct environment with its own rules, not simply as a colder, thinner version of the solar wind. So where does that leave things as of 2026? Scientists now have a working, well-supported explanation for the hum, quasi-thermal noise, generated primarily by a small population of fast interstellar electrons, layered on top of the ordinary background plasma. It isn't the kind of answer that makes for a dramatic headline, nobody found an alien beacon, and nobody rewrote the laws of physics. What they found was something arguably more useful, a reliable, ongoing measurement technique. Because the mechanism is now understood, scientists can use the strength and shape of this signal to directly calculate the density and temperature of the plasma surrounding Voyager 1, without needing to wait for a rare shockwave event to pass by. That turns what started as a confusing anomaly into a genuine diagnostic tool, a way of taking the interstellar medium's temperature, so to speak, every few days instead of every few years. That matters enormously right now because Voyager 1's instruments are running out of power, one at a time, as its plutonium-based generators continue their slow, irreversible decline. Every instrument still operating is providing data that can't be replaced once it's switched off. Having a technique that lets a single, already battered plasma wave instrument continuously monitor the density and temperature of interstellar space, rather than sitting silent for years waiting for the next shockwave, means the spacecraft's remaining, dwindling power budget can be stretched to deliver more usable science per watt than anyone originally expected. The explanation also opens a new, more specific question that wasn't even askable before. Where do these superthermal electrons come from in the first place? Candidates include energetic particles accelerated by distant, ancient shockwaves rippling through the galaxy, or particles connected to the broader population of galactic cosmic rays. Answering that fully will likely require a dedicated future mission built specifically to study interstellar space. Something like the interstellar probe concept currently being studied by the Johns Hopkins Applied Physics Laboratory, which would carry instruments purpose-built for exactly this kind of measurement, rather than borrowed decades later from a spacecraft designed in the 1970s to fly past Jupiter and Saturn. Until a mission like that exists, and it would take decades to reach the same distance Voyager 1 already occupies, this repurposed 40-year-old antenna, and the quasi-thermal noise physics finally worked out to interpret it correctly, remains the only continuous window humanity has into what the plasma between the stars is actually doing moment to moment. There's something quietly satisfying about how this particular mystery ended. It didn't get solved with a dramatic new discovery or an exotic new particle. It got solved the way a lot of real science actually gets solved, by taking an old tool built for a completely different job and carefully, patiently working out exactly how to trust what it was telling you, while staying honest about where that trust could go wrong. The signal itself was never a message, and it was never a mystery in the sense of something requiring new physics to explain. It was the ordinary background hum of interstellar space, generated by physics that had been understood in the solar wind for decades, applied for the first time to an environment nobody had been able to listen to directly before. What made it remarkable wasn't the sound itself. It was that we were in a position to hear it at all because one aging, unglamorous instrument built before most current astrophysicists were born happened to still be running 15 billion miles from where it was built, in exactly the right place at exactly the right time. The hum is still there. It's still being measured, still being used to track the slow, ongoing churn of the interstellar medium as Voyager 1 continues its journey outward. And somewhere in that steady, patient signal is a reminder that not every unanswered question needs something new to explain it. Sometimes it just needs someone willing to stare at the plot a little longer and trust what they're seeing. If you want to understand what this signal keeps revealing as Voyager 1 pushes farther into interstellar space, subscribe and turn on notifications. Drop a comment with what part of this explanation surprised you most, and share this with someone who'd want to know that we've been listening to the sound of deep space for years,